Sooraj Nair from Arizona State University, and they will be presenting a talk titled Exploring the Influence of Material Characterization and Extruder Geometry on 3D Printing of Cementitious Binders. So with that, take it away.
Thank you. So good day, everyone. I'm not sure which part of the world so people are attending has joined from, but I hope everyone is doing well. My name is Sooraj, and I'm a PhD student at Arizona State University. I'm presenting a work that we did quite a while back, focusing on correlating the material and extruder geometry characterization for cement paves specifically. So this is done as part of my PhD thesis, and yeah. So mandatory first slide on concrete 3D printing. We saw several speakers giving background. I just wanted to state the fact that we have different levels of testing, lab scale based to where we do a trial and error to adding the aggregates to get lab scale mortars. We test them in printing to characterize different properties for these binders. Finally end up with if it is printable, like the printability of the mix. And then we take it to on-site printing. Now, lab scale mortars, again, we've seen, again, other presentations where coarse aggregates are used, which is very good. So ultimately, the point that I'm going to make is, given a set of binder components and a system, given a set of binder components and a set of systems that we could use, like how do we decide what is the right mixture and the right system that can provide a reasonable or good printing output? So that's the question that basically we asked, and then this whole presentation will be split into like 3 sections. One is the rheology part of the binder. Second is the geometry or the system part of the extruder, and the third is the post-print quality of the binder. Now, what we'll also be focusing will be on extrusion using a barrel die system and not a screw extruder system, but this study could be extended to that as well. So we've identified a few paste, starting from plain OPC and then to a 30% fly ash replaced bindery mix, and then a 30% limestone replaced bindery mix, and then a limestone and silica fume replaced 15% each mix, and a binary limestone replaced mix with super plasticizer. We identified the yield stress in the plastic viscosity using standard parallel plate rheological testing. We also again did a printing experiment for all these mixers to find that the plain OPC in the state where it was extrudable was not buildable, of course, and it was failing with discontinuities in the mix. The fly ash mix, where it's pretty much printable, but the shape stability was not much, so it was failing in plastic collapse much early. Whereas the limestone replaced mixes were pretty good, so that's why these 3 mixes are in the study for the sake of presentation. Also are qualified printable, while these are non-printable. But we just want to see how the properties that we're going to discuss later is different across these 2 regimes of mixes. Now, generally, we have identified that this is again in the range of 50 to 350 pascals, and research shows that we need at least 150 pascal for yield stress for these mixes. Now, so the second part where we look at the extrusion characterization, we have a standard setup again, which has a barrel die geometry. This is where the material go in, and then we push the ram at a specified speed, and we record the force needed to extrude versus the ram displacement value. Now, the graph generally has 3 regimes. One is a pre-consolidation regime where the material is consolidating slowly, and then it kind of comes to a steady state condition where if there is plastic deformation happening from the barrel to the die, where you see that the pressure is almost steady or is slightly increasing depending on how the material is. And then towards the end, when there is a dead zone where the material which is stagnant near the barrel because there is constriction from the barrel going to the die, there's a dead zone region. And when the ram reaches the region and the dead zone collapse to induce radial material flow, the force increases. Now, how these three regions and the pressures come in can be used for extrusion characterization, which is it is established. Now, we bring together the material and the extruder characteristics together in the next stage, where we take a standard geometry of the extruder. Now, the changing values that we do different types of geometries, and the values that we change will be the die entry diameter, the die exit diameter, and the length of the die. So when we change it, basically the system is changing, and we are checking how the material respond to a changing system. So we have identified 5 different geometries depending on different combinations of these 3 parameters, and then the 5 mixes that we just talked about are also taken, and we subject it to an extrusion test to find the ram force versus displacement response. And you could see that there are different types of graphs, different response that the same mix, excuse me, the same mix give for a given set of geometries. Now, these are being correlated using a geometric ratio that we are establishing in the study. So the geometric ratio is kind of a quantifiable number that is characteristic to a given system of a barrel die geometry. Now, this is based on the 3 parameters that I've talked about just now: the entry, the diameter, and the die length. Now, this lump sum number can be is put in a way that it can be generalized for any different type of geometry, be it an orifice, a uniform die, or a tapered die. And for the given or selected geometries in this study, which is a 10 mm or a 4 mm diameter and a consistently 36 mm length die, we have an increasing geometric ratio from O10, orifice 10 to orifice 4, and then comes a tapered nozzle, and then a 10 mm uniform die and a 4 mm uniform die. So this geometric ratio is kind of indicative of the constraint on the extrusion and the particle rearrangement that a material will experience. So what we did was we took these 5 mixes, we subjected to 5 different types of geometries. Then we get the extrusion pressure versus displacement response. We can see that with respect to increasing geometric ratio, your steady state pressures generally goes up or increase. So generally, that's the trend that we see. At the same time, the dead zone length, which is the stagnant portion at the end of the barrel, it tends to increase with respect to increasing constructivity or the geometric ratio. So your graphs, the increasing portion or the exponential increase portion shifts to the left when you have a higher geometric ratio. Now, the dead zone length is generally characterized using the point where the curvature significantly increases. Now, we generally see that the steady state pressure and the dead zone length generally increases with the geometric ratio. So the good mixtures or pretty what do you call it, invariable response, gives an invariable response to the changing geometry. For instance, this is the limestone and the microsilica induced mix, which pretty much doesn't show any variation with respect to changing geometric ratio. We'll discuss about it a little bit more in detail later. But I'm going to introduce a little bit more on the dead zone formation mechanism, which we have identified. So generally, we think that the dead zone forms as the material starts extruding and when it reaches a steady state pressure, until it reaches a steady angle where the material here is stagnant, and then the rest of the material which is in the barrel shears out around this region into the die. But what we have identified in several of these mixes, especially in non-printable mixes, are there is liquid filtration that induce a build-up in the dead zone, not just in an angular fashion, but in a linear fashion as well. So during extrusion, you'll see that if a material is susceptible to liquid filtration, you'll see that more and more linear build-up of the material happen. Plus, the material will have an angular region which is dependent on the angle because of the particular mixture that we are using. So the non-printable mixes generally show a very high dead zone length, especially with progressing extruder RAM. So from the extrusion characteristics and the rheological characteristics, we also check the post-print quality. This was shown earlier. What we do is we print typical filaments of 4 by 6 and 4 by 6 diameter filament dimensions, so layer height by layer width, and then we see what the area printed is versus the find the ratio with respect to the design parameters. So it's more like solidity ratio that has been established in literature. So that ratio is being used to find how well the post-print output quality is. So stable output for printable binders give pretty much a good flow ratio, which I'm going to show later. So which is the limestone-based binders, and they tend to show better particle packing and lesser water filtration. So what we generally see is with respect to increasing geometric ratio, the steady state pressure tend to show a power law relationship for a given mixture. And for OPC and fly ash mixers, they're typically very high, especially even in the lower geometric ratio. So even with very open-ended or kind of less constrictive geometries, the non-printable mixers generally show a higher steady state pressure, whereas the printable mixers show a lower one. But for better particle packed mixes, like for instance the ternary blend that we used, just like what Dr. Wilson had earlier discussed, shows an invariable response with respect to an increasing geometric ratio, which is shown over here. Now, the mixers generally have either a higher dead zone length region or a lower dead zone length region. So, the printable mixers generally show a 15 maximum dead zone length, whereas it's almost double in the case of non-printable mixes. So, and this is especially attributed to the water filtration effects that is happening. So we could take, if we take the dead zone length and the steady state pressure together, there also is a correlation. Generally, again, if you have a higher steady state pressure, the chances for a dead zone length to build up more is much higher. But then there is a marked difference, just like we saw earlier, that printable mixes generally show a lower dead zone length, although steady state pressures could range in a higher variation, because as you increase the conductivity, even the good printable mixtures could show a much dependent behavior on the geometry and could show a higher steady state pressure. If you take the steady state pressure, which is again a proxy for extensional yield stresses that researchers have established, the ratio of the steady state pressure versus the yield strength also can be taken as a measure to see if a mix is good in printability or not. So if we do that with respect to the geometric ratio, again, the super plasticized mixers, which is the L30S, or the ternary blend, tend to show a very constant or rather invariable relationship with respect to geometric ratio. That just means that the mix has much more flexibility in using in a wide range of geometries. Um, so this could be a potentially beneficial mix or set of mixes, and this can be used for a given mix for a set of geometries without any much trouble in terms of the steady state pressure and the dead zone length. Now, the flow ratio that I defined, talked about earlier, which is similar to solidity ratio. So we take the actual print dimensions divided by the designed print dimensions. We can see that there is a marked reduction as you increase the geometric ratio, especially in the case of non-printable mixes, whereas the printable mixes generally, they stay around 1, which just shows that the area of the printed filament is more or less the same as what we had in the design mix. So this just shows that the higher requirement for the steady state pressure is restricting the mixture to flow, and there is a lot of liquid filtration, so the particle packing will also be much lower. So your effective area that you find in the post-print output will be much lesser. So it is just an indicator that improved particle packing in this case is a 1.5 micron limestone binder or filler can help in better output quality. And then we can see that there is a larger flow ratio or deviation just means that there is like more defects or layer instabilities, just like in this case where you don't have a uniform filament, but rather varying filament. This is more visible in the case of higher geometric ratios. So to summarize, what the study puts forward is a unique geometric ratio which can basically quantify a given system, and then we can use that as a measurable quantity to identify which range of geometries are suitable for a given mixture. So the printable case generally demonstrated an invariant flow. So the slope, if you find the steady state pressure variation with respect to geometric ratio, the variation with respect to the increasing geometric ratio is much lesser for a printable paste when compared to non-printable paste, which will have a much higher increase with respect to slight variation in the geometric ratio. So the dead zone length and the stress ratios are convenient metrics again to evaluate the quality of the print. Because the higher dead zone length is effectively showing that your material will effectively build up much more due to liquid filtration inside your extruder, and then your effective volume of extrusion will also reduce. And the stress ratio effectively shows with respect to the steady state pressure and the yield stress of the material if the mix is like appropriate for the given system, like the extruded geometry or not. So generally, again, binders with SEMs like the limestone and silica fume gives better particle packing, and they tend to show suitability for printability. So more details are in this paper which we have published earlier, and I thank NSI for funding the research and our team for helping in this research. And I'll be more than happy to take some questions. Thank you.
All right, thank you. We have about 3 minutes for questions. It says, will the dead zone degree also influence the results? From literature, it was suggested within a range of 40 to 60 degrees.
So I didn't actually catch the question clearly. Sorry.
I'm sorry. It said the question, as written, says, will the dead zone degree also influence the results? From literature, it was suggested within the range of 40 to 60 degrees.
Oh, so the angle. Okay. Yeah. Yeah, understood. Yeah, that will definitely affect the results. So, for example, in the case of the super plasticized mixes or the ternary blends that we have used, we can see that the angle is like much lesser than 40 from what I've seen, like somewhere around like 30 or 25. So it's just depending on how the mixture integrity is how that angle of repose is like defined. So although typically like 40 to 60 years, 60 years like stated in the literature, but we have noticed is we could like reduce it when we ideally or properly proportion the mix. But definitely yes, like that angle will have an influence on the results. Yes.
Okay, thank you. The next question, can you comment on the effect of viscosity on dead zone increase? It seems that your later mixes have higher viscosity, which causes pumping problems.
Good question. So as such, we didn't have a pumping scenario coming in this experiment because we didn't have a pumping system as such. But then for the viscosity, what I believe from the experience that I had is higher viscosity, of course, will be beneficial in an extruder point of view, but then it shouldn't be too high that, like the audience has said, should affect the pumpability. So if there is pumpability issues, we can have a limit on the viscosity parameter that is suitable for the pumpability, and then take that for the extruder geometric ratio relationship. So have a limit on that that value over here. So you might have a maximum limit on the geometric ratio depending on the maximum viscosity, which is possible for, or which is ideal for the pumpability part. So we'll have to do that limiting correlation based on the viscosity as well. Yes.
Excellent, thank you.